Hello, my name is Matthew Kolosick. I'm a PhD student at the University of California, San Diego, and today I'm here to talk to you about our work on achieving isolation without taxation. So, third-party code is everywhere, from media libraries in web browsers to edge computing networks such as Cloudflare or Fastly's. It even shows up in PDF rendering in iMessage. Unfortunately, this third-party code is potentially dangerous. In fact, it is often written in unsafe languages like C or C++, which means that it has potential memory bugs, which could become first-party bugs in, say, Chrome itself. In fact, recently, a heap buffer overflow in free type led to an exploit in Chrome that was being exploited in the wild. In iMessage, even more recently, the forced entry bug stemmed from these 4 lines in a third-party library used by PDF rendering that led to a zero-click exploit that was being used to target a Saudi activist. We worked together with Mozilla engineers to help prevent this issue in Firefox by sandboxing and this third-party code. So instead of libjpeg potentially being able to attack all of Firefox if there was an exploit in libjpeg itself, we employ a technology called SFI, or software fault isolation, that transforms the potentially buggy code to safe code. This works by taking the code in C or C++, compiling it through an SFI compiler, and then producing safe assembly that is safe to link in. This safe assembly is produced by adding extra structure and properties to the assembly, such as memory isolation and control flow integrity, to prevent these classes of memory safety bugs. Unfortunately, this isn't quite enough because we're still just running assembly. And that means that we have a number of shared resources, such as a call stack, callee save registers, and shared registers. So even if we no longer have memory isolation bugs, a bug in libjpeg is still overwrite the return address, change register values, or steal secrets from registers. To prevent this, existing SFI systems use what we call heavyweight transitions, which add wrappers to handle these shared resources. This essentially virtualizes these shared resources, such as providing a separate protected call stack, protecting callee save registers, and clearing all scratch registers. And then at the boundary between libjpeg and Firefox, these heavyweight transitions mediate between these virtual and the real resources, ensuring that bugs in libjpeg can no longer attack and steal secrets from registers or any of these other attacks. Unfortunately, there's some problems with these heavyweight transitions. First of all, they're expensive. We have to virtualize all of these resources, and they switch back and forth happens at every context switch. When we were trying to sandbox this add this SFI in Firefox itself, we found that the original unoptimized heavyweight transitions added up to a 400% overhead, and even optimized, it was still a 10% overhead for the transitions alone. Further, these heavyweight transitions are hard to implement. There's a lot of different processors, different calling conventions. Here's just a sampling of bugs related to that in the NACL SFI compiler, one of the most developed SFI compilers. Our solution to this is what we call the zero-cost transitions. So this takes the idea that SFI already added some structure. What if we just added a little bit more? And we define this extra structure as a set of zero-cost conditions. So instead, we have a zero-cost SFI compiler that produces a sandboxed SFI assembly with just a little bit more structure, ensuring that these bugs can't happen. And so these zero-cost conditions are defined as some extra structure that includes things like ensuring that clobbered state is saved and restored, removing a class of bugs entirely. Further, it ensures that these conditions ensure that the sandbox code cannot read confidential data. And to put this all together, we have an extra set of properties that ensure each of the functions within the sandbox library behave compositionally. Together, these zero-cost conditions ensure that this whole class of bugs cannot even happen, ensuring that we have memory isolation and secure isolated code without needing the heavyweight transitions. To guarantee this in Firefox itself, we split our SFI compiler into 2 parts. First, we take any compiler that outputs WebAssembly code. From there, we use the Lucet Wasm to native compiler to produce assembly that meets these zero-cost conditions and doesn't need heavyweight transitions. But we don't actually want to rely on these compilers, so we pull them out of the trusted code base and instead verify the native code, and we build a zero-cost verifier that we call ver0, which ensures that the compiled assembly meets both the zero-cost and SFI properties, ensuring that it is safe to isolate without need for heavyweight transitions. If you found this interesting, come see our talk to learn how the zero-cost conditions could save you up to 30% or more on your SFI costs.